Okay, continuing on with what we have in second order differential equations, and we're going to revisit what we have had here with a homogeneous second order differential equation, ay double prime plus by prime plus cy is equal to 0. And I said from the introduction that we will be looking at this through the lens of performing or arriving at the solution through algebraic performance. Okay, but again, for what we have in the case of y, so if I had, again, individually, like y equal to u, y equal to v, well, we would have a d squared u over dx squared plus b du over dx plus cu is equal to 0, and y equal to v, where I have a d squared v over dx squared plus b dv over dx plus cv is equal to 0. Individually, okay, this is what we would have in the solution for y at u as well as y at v, and we looked at through adding u and v together. Well, guess what? Individually, you have, with y equal to u, the equation's at 0. With y at v, okay, the equation is still at 0, and guess what? 0 plus 0 from the individual components applies also to the addition, again, where 0 plus 0 is equal to 0, and so we were able to arriving at the substitution of u plus v in place of y, where I had this set up. And again, just to illustrate that if y equal to u and y equal to v are solutions, but we also had the combination y is equal to u plus v. And now again, just going back to our original equation. Okay, so we have a d squared y over dx squared plus b dy over dx plus cy is equal to 0. And just creating a bit of a pathway to looking at solving in algebraic terms, and just kind of referencing what we had from the very start. And I tell you what, just looking at things incrementally. Okay, so let's say that if I have momentarily that a is equal to 0, well, this homogeneous second order differential equation is going to be first order, where I would have b dy over dx plus cy is equal to 0. And let's say that, just kind of like when we were looking at the integrating factor, I wanted the derivative to have no coefficient other than 1 in front of it. So if I were to divide this equation by b, so it would have dy over dx plus c over b times y is equal to 0. And if we let, say, a variable k be equal to c over b, well, we can rewrite this equation, whereupon we will have dy over dx plus ky is equal to 0. And for this first order differential equation, if I were to solve what I have here, okay, so again, just like the very first equations, okay, we can solve by separating the variables. So here we have dy over dx. I can isolate the derivative and set this equal to negative ky, and just have the terms of y on one side. So with division by y, I have dy over y is equal to the negative of k dx. And again, with the separation of variables, I can integrate. And what I'll do here, I'm not going to worry about the absolute value notation. I'm just going to cut to the chase. So you have what's going to be the natural logarithm of y is equal to negative kx plus a constant. And again, I'm looking at solving for y. So both sides of the equation are going to be powers to which the natural logarithmic exponential base e is going to be raised. So you have e to the natural logarithm of y is equal to e to the negative kx plus c. I'm going to say that just taking the reverse of the product property of exponents. So e to the negative kx plus c I can write as e to the negative kx times e to the c. And we'll say that we will have a to be equal to e to the c on the basis that we have the flexibility to say that we have a constant to a constant is equal to a constant. So we have, in this case, you have a times e to the negative kx. Okay, and again we have e to the natural logarithm of y, so this will go to y. So you have y equal to a times e to the negative kx. Okay, and now just now k could be a positive or a negative value, and I'm just going to rewrite this solution. So if I let, say, the letter m represent negative k, so we'll just say we have y is equal to a times e raised to the mx. Okay, and so going back to what we have with our homogeneous second order equation. Okay, so if you notice, we have in the layout, okay, so you have just for the general solution, okay, so you have y equal to a times e to the mx, and lining things up here. Okay, so you got y is equal to a times e to the mx. And for what we have in the case of the first order derivative, so again, we have y prime equal to dy over dx. And so that is going to be a times m times e to the mx. Again, just for y double prime, or d squared y over dx squared. Again, taking the derivative of am e to the mx with respect to x, so this will become am squared times e to the mx. Okay, and so substituting what we have here. Okay, so we got a times uppercase a m squared times e to the mx, and we have plus b, okay, dy over dx, or by prime, and that's going to translate to a times m times e to the mx, and we have plus cy, so it's going to be c times a times e to the mx is equal to 0. And notice we have the greatest common factor will be uppercase a times e to the mx. So for what we're going to have in the rewrite, so we're going to have am squared plus bm plus c is equal to 0. Okay, so for this quadratic equation, Okay, so we're going to have up to 2 characteristic roots, okay, on the basis that we had them to be non-repeating. And okay, so we can say that on the one end, okay, so if we individualize, okay, so we can say that we can let m be equal to m sub 1, and that m be equal to m sub 2. Think of like the quadratic equations, like solving for x, like you have whether you are using the completion of the square, or looking at the zero product property, or using the quadratic formula. You have like your two solutions, like x sub 1, x sub 2, same kind of thing here. And so we have one solution is going to be like y is equal to a times e to the m sub 1x, and another solution we have that y is equal to, and we'll say that we have b times e to the m sub 2x. Now think of like m sub 1 and m sub 2 as being analogous to what we had whenever we were itemizing, say in the earlier case where we had y equal to u, y equal to v, and we also had, you know, coupling together the sum of u and v, like we had our solutions, like where we have y equal to u is one solution, y is equal to v is another, and also we have as a tertiary solution y equal to u plus v. Okay, well guess what? We have y equal to a times e to the m sub 1x, and y equal to b times e to the m sub 2x, and I can sort of alloy these together. So this is one solution, this is a second, and just consolidating, we say also that y is equal to a times e to the m sub 1x plus b times e raised to the m sub 2 times x.